Hi, this is Chloe. I'm going to be teaching about thermodynamics, and the first lesson video is going to be over heat, ideal gases, and phase changes. So heat is not internal energy. Internal energy is the total energy possessed by the particles in a sample, including total kinetic energy due to random motion of the particles, as well as the potential energy the particles have due to the positions they have relative to each other. And we know that the symbol for internal energy is U, according to College Board. And as well, internal energy is transferred from a hot to a cold subject. That is the heating process. So its process cannot be possessed, just like force. And so Q is going to be the symbol for heat. And heat is not temperature. Do not say they are the same. This is the biggest misconception. Honestly, before I was told this, I just related heat with temperature, but temperature is actually the average kinetic energy of the particles, and we'll talk about that later. It's going to be measured in joules, and we'll talk about how to get that later as well. But so now we're going to be talking about ideal gases. There's going to be some relationships. There's actually this gas lab called PhET that I'm going to be linking, and it just shows the relationships and how to find them. It's great for visualizing it because it doesn't make that much sense at first, but it just takes forever to use the lab, so I'm not going to be using it right now. What you need to know is these four different relationships is going to be important when you learn the first law of thermodynamics and the different processes, um, the heating processes and all of that. So pressure and volume. Whenever you increase pressure, the volume is going to decrease and vice versa. So as you see, as volume gets greater, pressure decreases. And you can see that with, I don't know, I'll think of another example. But next is going to be volume and temperature. This one's really easy to think. Oh my God, I keep forgetting about this. I'm sorry. We're going to go back here. So if you think about heat, it's like a process. So whenever you have your hand on what feels like to you cold is also something that's not like an energy, it's not possessive, it's just what you are feeling like compared to your environment. It's actually cold is just you losing energy to something else. Like you're giving away your energy. That's what you feel when you are cold or you touch something that feels cold. You're actually just transferring your energy from your hand or whatever you're touching with to the object. And so whenever you're touching a surface and it feels cold, you're transferring your energy. That is going to be a heating process. So that's the example that I forgot to use. As you can see here, I have this little space that is intentional. You cannot have zero volume, at least not in this class, physics 2. Maybe it exists somewhere else. I'm pretty sure it doesn't, but I don't know everything about physics, but I do know that in physics 2, you can't have zero volume. You can have zero pressure. That's going to be vacuum, but that's why I can touch over here, but we're not really dealing with that much. But so you can't have zero volume, which is why it doesn't touch the x-axis. And this is going to be important later whenever we talk about the next video. But so whenever you increase your temperature, you're going to be increasing the volume. And that's whenever the pressure is staying the same. The constants are important to note because the temperature is going to be staying same for here. In this table down here, it shows all of this, which I will show in a second. But if you don't have this constant, everything's just going to be moving around. So you need a constant. So whenever you have temperature the same, pressure and volume have an inverse relationship. Whenever you have pressure and moles the same, which is just like the number of particles you have is going to be in all of these, except for this last one. But if the pressure is the same, the volume has to increase because over here, pressure, when temperature increases, pressure increases. You see this whenever you leave like a can of soda in a hot car or something, and then it explodes. That's because the pressure becomes so great because the particles are moving so fast and the pressure is like it's force over area. So now you have a bunch of force for this area and it just becomes so great. and you can't change the volume, so it explodes. The volume stays the same here, pressure stays the same here, and temperature and pressure stays the same here. But so that's going to be a direct relationship. And with the last one, you find Avogadro's law. So the more particles you have, the bigger volume is going to be if you keep temperature and pressure the same. And you can see here all the relationships. And next, we're going to be moving on to the phase changes. And so if you have a solid ice cube sitting on a counter and it's melting, that's actually because its energy is, it's taking energy from the environment. So its energy, amount of energy that it has is increasing, and then it moves on melting into a liquid. So whenever you move across here, you're increasing energy. And whenever you move across here, you're decreasing your energy. So that's why you know that gases are going to have the most energy and solids are going to have the least amount of energy. And so that's just something to keep in mind. So solids are going to have less than liquids, which have less than gas. And so the particle motion of gas is going to be very high, which is also why they, because kinetic energy is half mv squared, so their velocity is going to be higher. The particles are going to be bouncing around more. Whenever you have solid, the particles are really like close to each other. They're super close, which is why the velocity is just not really that much. And so with liquids, you have some more velocity because the particles are more free to move, but it's not as much as gas where it's super like bouncing around. And the greater you have the temperature, the more these gas particles are going to be moving around. And so our first equation is going to be PV equals nRT. It's on your equation sheet. And P is going to be pressure, V volume, N is going to be moles. And just as a reminder from chemistry, 6.02 times 10 to the 23rd of a substance is going to be 1 mole. And R is a universal gas constant, as we can find here. If you have PV equals nRT and you divide this, you get R. And so this graph over here is a PV over NT graph. And so since you find slope is going to be PV over NT, which is right here, it's just the slope is R, which means it's a constant. And so it's going to be 8.31 joules over mole K. And you use that in your equation, and temperature is going to be measured in Kelvin, like I mentioned earlier, 273.15 plus Celsius in degrees is going to be Kelvin. So our first problem here, we're going to redo it. This is the second time I made this video because I forgot so many things. So we have our equation, PV equals nRT. So we know our number of molecules. We're going to have to convert that to moles because N is moles, but it's up here. And 600 centimeters cubed is going to be our volume, but we're going to change that to meters cubed because you need to do that. And we're looking for pressure because, oh, I should probably read the question. 1.88 times 10 to the 24 molecules of oxygen gas is distilled into an evacuated 600 centimeters cubed container. What is the gas pressure at a temperature of 423 Kelvin? So just follow along, try and solve this problem if you want first, and then play the video, or we can go through this together. So we start off with our equation. We look for our givens, which is going to be volume, molecules, which we're going to convert to moles, and then temperature. And so the variable we're looking for is pressure, since R is a constant, and we know that as well. So it's going to be P times V, and so we have to convert that to meters cubed. And so 600 centimeters, so 100 centimeters is going to be 1 meter. So we divide by 3 times because it's going to be cubed, because that's what volume is. It's going to be length times width times height. Right? Okay, it's just going to be whatever. So that's going to be 60, so it's 0.0000. There we go. equals, now we have to find the number of moles, so 1.88 times 10 to the 24 molecules. And we know that 6.02 times 10 to, what is it? 23 molecules is 1 mole. So that equals 3.12292 moles. And R is 8.31. And we know that our temperature is 423. So some algebra. P is going to equal 1.82958 times 10 to the 7th pascals. And yes, so our next example is consider a gas that is sealed in this container. So this is going to be the stopper up here. I don't know if you can see me drawing on that. So we know that the number of moles is going to stay the same. So the number of particles was going to stay the same, but whenever you push, we're going to be pushing down this stopper lid down over here. And so whenever the volume decreases, the pressure is going to increase. As I said earlier, pressure has an inverse relationship with volume. And one of the most important things, I can't stress this enough, I use this so many times on tests, is you can create relationships because you have this. So we know that when PV equals nRT, PV over T is going to equal NR. Since NR is the same, you can set them equal to each other. It's similar to, like the equation of continuity, with fluids, how you could set A1B1 to A2B2. Since it's the same, they have a constant that they share with each other. You can set all these the same whenever you don't know it. So this is like, if you take anything away from this video, this is what you want to remember, and you can always take this out. So for instance, okay, I'm going to stop here. Actually, I'll talk about these relationships. I was going to say something, but after we learn the first law of thermodynamics, I'll talk about that. But also, the last thing is, whenever you don't have, like, they don't give you moles or something, and you have a number of molecules, and you just can't get to moles, okay? You just have a number of particles. There's actually this thing called Boltzmann's constant. It's this guy, since moles, like NO is moles, and N is molecule, so Avogadro's number is going to be Avogadro's number. So as you can see here, that equals N, but sometimes you'll just be in particles and you just can't get moles. So in that case, you're going to be using this equation here, because Boltzmann's constant is just this guy who put two constants together. R is the universal gas constant, and naught is going to be Avogadro's number. So this is actually going to equal something like, what is it? Oh, it's 1.38 times 10 to the negative 23rd joules over Kelvin. So that's going to be Boltzmann's constant, and just use that. And that is all for today. And I hope you learned something. Oh, actually, it's not. So just these questions to let you think about. When water freezes, is the energy absorbed or released by the water? Just take a moment. It's actually going to be released. So as we mentioned earlier, whenever we're up here, it's moving down this way if you're going to freeze. So it's releasing its energy in order to get to this state of a solid, because it's going to have less energy. And when ice melts, energy is absorbed from the environment in order to reach the state of melting, going to a liquid. And something else is, why does sweating cool you down? So you take the energy from, like, the water evaporates on your skin, and because it takes the energy from your skin, the liquid gains energy from the blood rushing to your skin, which is the temperature is increasing, and therefore the average kinetic energy is increasing, and the water evaporates. So it takes that energy from your skin, and so that leaves your skin, and which makes you cool down, and it uses it to evaporate. So that's just something to think about. And yeah, just let me know if you have any questions.